continuing this, no, if we evaluate the definite integral, we would get 2a h cubed over 3 plus 2ch, no, y. We just plug in, no, h and negative h to x, no, the x. So expanding this, we can get a times h cubed over 3 plus b h squared over 2 plus c times h minus, no, if we evaluate now with negative h, no, so that's a negative h cubed over 3 plus b negative h squared over 3 plus c negative h, no. If we simplify this, b of a bh squared over 2 would just cancel each other, no, and the a and the c would just add up, no, since if we expand a negative to raised to a third power, that would lead to a negative number times a negative number that would lead to a positive number. So it's just addition. Same with the c times negative h. That's a negative number times a negative. So that would become positive. No, so we would just add ch. So that would leave us with 2ah cubed over 3 plus 2ch over 3 times 2ah squared plus 6c. No, let's try to take note of this equation as we will encounter it later on. Moving on, recall our function f of x equals ax squared plus bx plus c. No, if we evaluate f of x at the nodes x naught, x sub 1, and x sub 2, we would get these. Since we have established earlier that the values of x naught being negative h, no, on the number line, x sub 1 as 0 since it's at the origin, no, and x sub 2 as h, the other end of our evaluation. Substituting these to the x's, no, we would get f of x sub 0 as a times negative h squared plus b times negative h plus c, which would lead to a h squared minus bh plus c. For x sub 1, no, um, the those with x's would just cancel out since they're just 0. Would leave us with just c. For f of x sub 2, no, that is a h squared plus b h plus c, no. Similarly, we could add these function evaluations, no. Say f of x naught plus 4 times, no, f of x sub 1 plus f of x sub 2, no. That would lead us to ah squared minus bh plus c, this one, plus 4 times f of x sub 1, so c. Then f of x sub 2, no, ah squared plus bh plus c. What would we get? No, we would get 2a h squared, no. We would just cancel out bh, and these the those with c would add up to 6, no. Isn't this familiar? 2a, 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 h squared plus 6c is the quantity we multiplied to h over 3 from earlier. No, from our two calculations, we can say that the area under the curve can be estimated as a third of h, no, times the quantity of the summation of f of a and f of c plus 4 times f of b. We just substituted a, b, and c as x naught, x sub 1, and x sub 2, no? So it's just the same. Now, what if we want to use a cubic polynomial instead of quadratic? That would bring us to the Simpson's 3/8 rule. Simpson's 3/8 rule uses a cubic polynomial interpolation with four equally spaced points, no? A, B, C, and D, denoted as the area under the curve approximately 3/8 of h, no, multiplied to the quantity of the summation of f of a and f of d and thrice f of b and f of c. The weights here are 1, 3, 3, and 1, reflecting cubic interpolation. This rule is particularly useful when the number of subintervals, no, is a multiple of 3 because of the way it divides the interval, no. So it's divided into 3. From A to D divided into 3. That would lead us to A, B, C, and D. You can also remember this symmetry, no, 1, 3, 3, 1 from Pascal's triangle if we expand it, no, from 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, no. Finally, we'll look at Boole's rule, which uses 5 points and a quartic polynomial. No. Boole's rule uses 5 equally spaced points fitting a quartic polynomial naman, no? Fourth degree. It's more accurate for smooth functions, but then again requires more function evaluations, no? It's denoted by the formula 2h over 45, no, times the quantity, the summation of 7 times, no, f of a and f of e plus 32 times f of b and f of d plus 12 times f of c, no. We're working now with 5 nodes, no, a, b, c, d, and e.